So the final example we're going to look at here is in my live lessons repository in the Java 8 EX16 folder. And here's the IntelliJ project for this particular example. We're going to go ahead and take a look here at the EX16 source file. And this program shows off a whole bunch of different ways to compute factorials for big integers, as well as demonstrate the performance of different parallel and sequential algorithms, as well as the danger of sharing unsynchronized state between threads. And I should probably say unsynchronized mutable state between threads. And it'll illustrate a bunch of other stuff. Some of the stuff goes beyond the scope of what we're covering right now, so I'm going to skip over it for the time being. In addition to showing sequential and parallel streams, it also shows off some really cool parallel processing features and sequential processing features of RxJava and Project Reactor. We're not really going to take a look at that right now because we haven't talked about that in the course yet, but it's interesting to see it. So let me go ahead and start running the program. This will take a while to run also, so let's let it run out while we look at the actual code. So we're going to use big integers here, and the reason for that is that factorials grow very quickly. And so if you try to compute a large factorial, then you'll quickly overflow the number of bits in a long, for example. And we want to compute the 1,000th factorial. So you can imagine that's a pretty darn big number. And in fact, let's see, there we go. It's in the midst of running. So these different mechanisms are computing the factorial for 1,000. And you can see just ridiculously how long that value is. That's continuing on and on and on and on for quite some time. Okay, and then also we'll see that this particular program, as usual, records the time taken for each of the different algorithms we're running. And we'll see that, for example, the sequential factorial using just a good old Java loop takes about 3,394 milliseconds. And the parallel versions are substantially faster, basically about twice as fast. But then we also have some other versions in here. We have some Buggy versions that are deficient for various reasons. And despite the fact that they're faster, they're wrong. So it doesn't really matter if they're faster. They don't compute what we want. And we show off a whole bunch of different things. So we're going to take a look at the different implementations and look at the results. So as usual, we warm up the fork join threads because otherwise we get weird results the first time we run stuff, because the fork join pool in parallel streams and in general is something that warms itself up as it's used. So there's sort of this overhead of using it initially, and then you amortize the performance once you've done it more than once. So let's take a look at the simplest way of computing factorial. This is the way you probably learned when you were taking an algorithms class. We start out with a big integer of the value 1, and then we go into a loop, and we keep looping until we're less than or equal to the value of n, which in this case is 1,000. And every time through, we take the current value and we multiply the current value by the big integer value of the loop counter I, starting at 2. So that's a very simple way of computing factorial, but it's also kind of boring. And most importantly, it doesn't scale. So let's go take a look at the sequential streams implementation. So this version is correct. It's not the fastest way to do it, but it works. And the way it works, which is more scalable, as we'll see in a moment, than the accumulator anti-pattern version we saw here, this goes ahead and makes ourselves a stream of values from 1 to n inclusive. It takes each of those values, because they're longs, and converts each of those values into a big integer. And then we use the good old terminal operator reduce, passing in the value 1 as its seed value or its initial value, and then passing in the big integer multiply method as the accumulator. And so what it's going to do essentially is it's going to combine all the elements in a pairwise fashion until we compute the factorial using the reduction mechanism. And that indeed works correctly. If you take a look at the results up here, you can see that the sequential factorial using a loop and the sequential factorial using sequential streams give the same result, except the one that uses a loop is a little bit faster than the one that uses streams. So you can see that there's a little benefit of using kind of a naked for loop when you're using traditional Java versus sequential streams. However, the key point of all this is not to compare a sequential loop with sequential stream, it's to compare a sequential loop with a parallel stream. And so I think that's what I'll do next, just for kicks. I'll just show you the parallel stream version of this, which looks pretty much identical to what we did before for the sequential version. The only difference is we slide in the dot parallel operation here, and therefore all the operations then run in parallel after that. So this map runs in parallel and the reduce runs in parallel. And as a consequence of doing that, you can see that the parallel stream factorial version executes substantially faster than the sequential version, basically twice as fast. And it's essentially about twice as fast as the sequential loops version, demonstrating the real benefit of streams. It's nice to get the benefits of abstraction by using sequential streams, but it's even nicer to get the benefits of parallelism by using parallel streams. And you'll see we have a couple of different implementations of the parallel streams factorial, one of which uses the 2-parameter version of reduce, and the other which uses the 3-parameter version of reduce. And you can see that the results are really the same. And you can see that by looking at the results here. They're very close together. They're 20 milliseconds apart, which is essentially in the noise. Notice that there is no shared state whatsoever in both of these versions of parallel streams that are using reduce. Reduce is cleverly designed to not have to worry about sharing of mutable state. So it guards against all these other problems we're about to look at. So what are some problems? Well, let's go take a look at some other ways to do factorials. And we're going to look at 2 buggy ways and 1 slow way to do parallel factorials. So here's the first one. This particular implementation is called Buggy Factorial 1, and it's got a nested class called total. And total is going to have a field. It's a running total of the factorial, and it's going to have a method called multiply. And the multiply method is going to take the value n that's passed as a parameter, and it's going to update the running total of m total by multiplying m total by n. Looks pretty simple, right? And in fact, on a sequential stream, this works just fine. On a parallel stream, chaos and insanity will ensue because this is shared mutable state and it's being modified concurrently. How is it being modified concurrently? Well, if we look down here at the factorial implementation that's buggy, you can see we make ourselves one object of type total. And then we share that object between all the threads in the parallel stream. And so every time multiply is called, multiply is multiplying m total, but m total is a shared mutable field that's being operated upon by different threads in the common fork join pool. So as a consequence of this, the results are simply wrong. So if you take a look at the results for buggy factorial, you can see it doesn't match the correct results for all the other factorials that work properly. And there's some other problems here with returning m total in a non-synchronized way and so on and so forth. So don't do this. So this is an example where the shared mutable state is being modified here, and it's being accumulated in this way. There's another example called Buggy Factorial 2, which also uses shared mutable state in a slightly different way, but it's still a problem. So what we're going to do here is we're going to essentially create a parallel stream of long values from 1 to n, and then we're going to make a stream of big integer multiplier or BI multiplier objects by using the BI multiplier constructor. And we'll take a look at what a BI multiplier is in a second. And then down here, we're going to perform a reduction on BI multiplier. But BI multiplier, as you'll see, is not immutable. And reduce expects to be used with a immutable object. And this is not immutable, it's mutable. And because it's mutable shared state, and chaos and insanity ensue. So let's take a look at the multiply method. You can see that BI multiplier contains a big integer, which is not synchronized. And it has a constructor that converts the long into the big integer. That's okay. And then it has a multiply method that goes ahead and updates the big integer by multiplying it by the parameter that's passed in. And that's the problem. This is unsynchronized and it's mutable shared state, and therefore chaos and insanity will ensue when this thing is run in parallel. And in fact, if you take a look at the results for Buggy Factorial 2, it's also incorrect, although it happens to be somewhat different than the Buggy result from Buggy Factorial 1, demonstrating that you can make mistakes in all kinds of different ways. So those are some things not to do. Now, you might be tempted after taking a look, particularly at Buggy Factorial 1, you might say, well, gosh, can't I solve this problem just by synchronizing the multiply method? In which case, I don't have to worry about race conditions, modifying that shared mutable state. And the answer is you can do that, but it turns out to be an extremely bad idea. And so let's go ahead and take a look at synchronized parallel factorial. So this implementation is pretty much the same as the Buggy Factorial 1 implementation, except now we have a multiply method that's defined to be synchronized, which means that only one thread at a time can be modifying the M total count. So we've solved the problem of race conditions. We also solved the problem of visibility by making a get method that's also synchronized. And now, at first glance, our code looks the same as it was before, except when we run it, we're going to get the same result as all the correct versions of these parallel factorials. If you take a look, for example, synchronized parallel factorial has the same results as all the other correct implementations. But there's one big problem. Adding in that lock greatly slowed things down. And in fact, the synchronized parallel factorial actually ran substantially slower, like about twice as slow as the sequential implementations. So what this is showing is if you're not smart in where you put your locks, and you're not smart in how you address the issues of mutable shared state, you can actually make your program even slower than running it sequentially. And that's a really, really important lesson to understand. Namely, that using parallel processing is really going to work best if there's little or no shared mutable state. And if there is shared mutable state, then make sure you protect it in a more intelligent way than using that one lock approach we did here. And the reason why the one lock approach doesn't work well is because it becomes a single point of contention where multiple threads will be beating on that one particular lock from the different threads in the common fork join pool, and thereby slowing things down substantially, as we saw here. So we get the right result, it just takes an awful long time to compute it. So there's some other examples here, which I won't go through in the interest of time, but there's also some approaches that use parallel flowables and parallel fluxes, and they look very, very similar in this case to the parallel streams approach, although the actual implementation details are wildly different because RxJava and Project Reactor use reactive programming as opposed to synchronous parallel programming, which is what Java Streams does. We'll come back later in the course and take a look at how the reactive programming stuff works. So anyway, that's what I wanted to cover here with this particular example. It's a really fun example because it shows innocent mistakes can have big consequences. And it also demonstrates something very powerful about Java parallel streams, which is it works best when it can completely remove the need to do any kind of synchronization at all. If you take a look at the parallel streams implementation of Factorial, the one that's done here, you'll see that there's actually no shared mutable state, there's no locks, there's no overhead, and this all works by the clever way in which parallel streams and the Java streams framework divides the data up into separate chunks that only get merged together in the reduced phase in a very carefully controlled way that has very little overhead, which scales nicely and doesn't require you to know anything about synchronization at all.